25th of April, 1986, Chernobyl Nuclear Power Plant, Unit 4. A routine safety test begins at midnight, log pages stamped with shift codes as usual. Operators expect the RBMK reactor, graphite-moderated, water-cooled, a Soviet engineering achievement, to behave predictably at reduced power. Design documents promise stability. At 1:23 in the morning, control room instruments tell a different story. Power output drops to near zero, then surges uncontrollably. Radiation monitors outside the reactor building climb from background to 25 millisieverts per hour within minutes, 250 chest X-rays worth of exposure in 60 seconds. The reactor was never supposed to do this. Engineers had called the positive void coefficient manageable. Field readings now suggest otherwise. What began as a test of emergency systems became a test of the design itself, and the numbers were already rewriting the conclusion. Soviet planners in the early 1970s faced an energy crisis. Industrial expansion demanded megawatts. Uranium reserves were limited. The RBMK, Reaktor Bolshoi Moshchnosti Kanalny, high-power channel reactor, emerged as the solution. Its design was ambitious. 1,600 vertical fuel channels piercing a massive graphite core, each channel cooled independently by water. Graphite moderated the neutrons. Water absorbed the heat. The system was modular, scalable, and cost-effective compared to Western pressurized water reactors. Anatoly Alexandrov, director of the Kurchatov Institute, championed the design. The RBMK could be built in stages, adding capacity as resources allowed. It used natural uranium enrichment levels, reducing dependence on expensive enrichment facilities. By 1973, the first RBMK at Leningrad began operation, generating 1,000 megawatts electrical. Within a decade, 11 RBMK reactors operated across the Soviet Union. The design documents acknowledged a characteristic called the positive void coefficient. When water turned to steam, a void in cooling channels, neutron absorption decreased, reactivity increased. Engineers calculated this effect would remain small during normal operations at full power. The reactor would run hot, produce steam steadily, and maintain equilibrium. Control rods would manage any deviations. What the documents did not emphasize, at low power, with minimal steam production, the insertion of control rods could briefly increase reactivity before reducing it. The graphite tips of the control rods, designed to displace water and improve efficiency, acted as additional moderator. In the narrow window of low-power operation, this feature inverted the safety logic. A 1975 internal memo from the Ministry of Energy noted, "Operational experience confirms RBMK performance at rated capacity. Low-power transients require further study." The study remained incomplete. Construction continued. By 1983, Chernobyl's Unit 4, the newest installation, entered service. The reactor hall stood 30 meters high. Inside, a circular steel structure enclosed the graphite stack. Cooling pumps circulated 28,000 cubic meters of water per hour. Steam separators fed turbines generating 1,000 megawatts. Radiation shielding consisted of concrete and steel layers. Instruments monitored neutron flux, coolant temperature, and pressure at hundreds of points. The facility employed 3,000 workers across 4 reactor units. Design promised containment, efficiency, and safety margins. The numbers on paper looked solid. But paper could not predict how systems would behave when operators pushed them outside rated conditions. That test would come on a spring night in 1986. 25th of April, 1986, begins as scheduled. Unit 4's annual maintenance requires a shutdown. Before bringing the reactor offline, engineers plan to conduct a safety test, simulate a station blackout, and verify that turbine inertia can power emergency cooling pumps during the gap before backup diesel generators start. The test has been postponed twice due to grid demands. Tonight, approval comes through. Deputy Chief Engineer Anatoly Dyatlov supervises. Senior Reactor Control Engineer Leonid Toptonov monitors the control panel. Shift Foreman Alexander Akimov coordinates operations. The test protocol, approved months earlier, specifies maintaining thermal power at 700 to 1,000 megawatts during the simulation. This range ensures adequate steam flow while keeping the reactor stable. At 1 hour after midnight, operators begin reducing power. The reactor responds smoothly, descending from 3,200 megawatts thermal. Steam pressure drops gradually. Control rods withdraw to compensate for reduced power, maintaining reactivity balance. At 13 hours, power reaches 1,600 megawatts. The test is scheduled for later in the shift. Then grid controllers request a delay. Another station experiences unexpected load. Chernobyl must continue supplying power. The test postpones. Unit 4 holds at half power for 9 hours. During this hold, Xenon-135 builds up in the fuel. Xenon-135 absorbs neutrons intensely, a natural reactor poison. At full power, continuous fission burns off xenon as quickly as it forms. At half power, production exceeds burnout. Xenon accumulates. At 23 hours, grid controllers release Unit 4 for shutdown. Operators resume power reduction. The test protocol calls for stabilizing around 700 megawatts, but xenon has peaked. As power drops, xenon absorption increases further. Reactivity falls steeply. By 0 hours 30 minutes on the 26th, power plunges to 30 megawatts thermal, barely 3% of normal low-power operation. Alarm indicators light across the control panel. The reactor is poisoned, choked by xenon. To raise power, operators must withdraw nearly all control rods, removing neutron-absorbing material to overcome the poison. This action reduces the reactor's ability to shut down quickly if needed. Operational regulations specify maintaining a minimum of 30 control rods inserted at all times, the operational reactivity margin. Logs from that hour show only 8 rods remained inserted. The margin was gone. By 1 hour, power stabilizes at 200 megawatts thermal. Not the planned 700, but enough to generate steam for the test. Dyatlov orders the test to proceed. Instruments show the reactor configuration lies far outside normal operating conditions. Akimov raises concerns, Dyatlov overrides them. The authorization has already been delayed twice. The test will run. 4 main circulating pumps operate, pushing water through the core at maximum flow rate to maintain cooling. This exceeds normal operating procedure for low power, but the test requires it. High flow rate means less time for water to heat, less steam formation, and consequently higher reactivity due to the positive void coefficient. The reactor sits on a knife edge. Too much neutron absorption from xenon, barely enough control rods, excessive coolant flow preventing steam formation, and operators preparing to simulate a power loss that will trip the pumps. Test protocol anticipated none of this. The document assumed normal operating conditions. Instead, the reactor occupies a configuration untested, unvalidated, and unknown to its designers. The numbers exist only in the control room. In instrument readings, operators watch with growing unease. At 1 hour, 23 minutes, the test begins. The test sequence starts with a button press. 4 turbine stop valves close, cutting steam flow. Turbine inertia keeps generators spinning, powering pumps for 40 seconds before momentum bleeds away. In that window, diesel generators should start and supply emergency power. The test measures this transition, but the reactor responds to losing its steam load. With valves closed, pressure in the cooling circuit rises. Water temperature increases. Microscopic steam bubbles form in the hottest channels. The positive void coefficient activates. Reactivity climbs. Neutron flux increases. More fissions occur. Power begins rising. Control room instruments register the change within seconds. Automatic systems react, inserting several control rods to compensate. Power stabilizes briefly. Then it resumes climbing. The reactor's behavior defies the gradual response operators expect. At low power, with minimal control rods inserted and coolant flow disrupted, the system's feedback loops amplify instead of dampen. Toptunov sees neutron period indicators shortening, the time required for power to double. At 1 hour, 23 minutes and 40 seconds, he announces power excursion. Akimov orders an emergency shutdown, pressing the AISD 5 button, reactor protection system full scram. All control rods should insert, flooding the core with neutron absorbers. 211 control rods begin descending into the core. Their electric motors drive them at 40 centimeters per second. Full insertion requires 18 to 20 seconds. The first 4 seconds decide everything. Each control rod consists of boron carbide, a strong neutron absorber, attached beneath a 5-meter graphite displacer. The graphite section normally sits inside the core, occupying space that would otherwise fill with water. When a rod withdraws fully, the graphite displacer also withdraws, leaving a water-filled channel. When the rod inserts for shutdown, the graphite tip enters first, displacing water with a material that moderates rather than absorbs neutrons. Only after the graphite passes through does the boron carbide enter and begin absorbing. This design improves efficiency during normal operation at full power. The graphite displaces water that would otherwise absorb neutrons wastefully. But during scram from a low-power state, with rods fully withdrawn, the initial insertion replaces water with graphite across the entire lower core. For 4 seconds, reactivity spikes before boron carbide reaches the active zone. Operators did not know this. Design documentation never highlighted the effect. Engineers assumed scram would always occur from normal operating conditions, where rods were only partially withdrawn and graphite tips remained inside the core. No one tested emergency shutdown from a configuration with all rods fully extracted. Instrument readings show power rising. Neutron detectors max out at 120% of rated power. Actual power exceeds their range. Later calculations suggest 30,000 megawatts thermal, 10 times normal operating level, within 3 seconds of scram initiation. Fuel temperature surges past 2,800 degrees Celsius, the melting point of uranium dioxide. Zirconium fuel cladding reacts with steam, producing hydrogen gas. Pressure inside fuel channels exceeds design limits. At 1 hour, 23 minutes and 58 seconds, a vibration shakes the reactor hall. Then a sharp pressure wave. The roof structure flexes. Instruments go dark as cables sever. Emergency lighting activates, casting red shadows across control panels. 2 explosions occurred. The first, steam and hydrogen, blew fuel channels apart. The second, larger, lifted the 1,000-ton steel plate sealing the reactor top. The plate, designated Elena, after the engineer who designed it, rose several meters, tilted and fell back, settling at an angle. Core graphite ignited on contact with air. Fuel fragments scattered across the roof and surrounding area. Radiation monitors inside the plant showed readings above 5 Roentgen per hour, 500 times normal background. Monitors outside the reactor hall saturated their scales. Actual exposure levels remained unknown because available instruments could not measure them. Akimov and Toptunov, standing at their control panels when the explosion occurred, received doses later estimated at 16 grays, far beyond survivable limits. They remained at their stations, attempting to activate emergency cooling systems. Valves did not respond. Pumps registered no flow. The reactor's water cooling system no longer existed. At 2 hours, firefighters arrive from the plant's fire brigade. They see flames rising from the reactor hall and graphite chunks glowing orange on the roof. Radiation levels are not announced to them. Equipped with standard fire gear, no additional shielding, they climb ladders to spray water on burning graphite. Within minutes, several received doses exceeding 10 grays. By dawn, 28 firefighters and plant workers will suffer acute radiation syndrome. Over the following weeks, 28 will die from exposure received in those first hours. The reactor hall remains open to atmosphere. Fission products escape directly. Iodine-131, cesium-137, strontium-90, plutonium isotopes. Wind carries the plume northwest toward Belarus. No announcement goes to nearby towns. Residents sleep unaware. In Moscow, 1,300 kilometers southwest, phone lines transmit fragmented reports. Initial communications describe a fire, structural damage, and casualties. The word explosion appears in logs, but context remains unclear. Was it chemical? Steam? How much radioactivity released? Early estimates span 2 orders of magnitude. At dawn, the Politburo convenes. Orders go out. Form a commission, dispatch specialists, secure the site. By sunrise, the radiation field extends kilometers from the plant. Monitoring teams measure surface contamination at 4 curies per square kilometer, 40,000 times normal background, in fields north of the reactor. At 10 kilometers distance, dose rates exceed 100 microroentgen per hour. At 30 kilometers, readings remain 10 times above background. The numbers define a new geography. Zones will be drawn, evacuation boundaries calculated, access controlled by dosimetry instead of fences. But that mapping lies ahead. On the morning of the 26th, only the instruments speak, their needles pressed against stops, unable to register the full measure of what the RBMK has released. Pripyat wakes to a normal Saturday. The city, built to house Chernobyl workers, lies 3 kilometers from the plant. 50,000 residents begin their weekend routines. Children play in courtyards. Markets open. At the plant, smoke still rises from Unit 4's reactor hall, visible from apartment balconies. Some residents notice. Most assume a minor industrial fire, nothing unusual for a facility of this scale. At 7 hours, a health physics team from Kiev arrives by helicopter. They carry RKS-20 and DP-5 Geiger counters, standard Soviet civil defense instruments. On the ground near Unit 4, instruments immediately max out. The RKS-20, designed for civil defense scenarios, reads to 500 Roentgen per hour. It pegs at maximum before the team approaches within 200 meters of the reactor hall. They switch to survey mode, taking readings at increasing distances. At 50 meters from the destroyed reactor, fragments of fuel and graphite litter the ground. A single piece of graphite, roughly 10 centimeters across, generates a radiation field exceeding 20,000 Roentgen per hour at contact. Exposure to this intensity for 2 minutes delivers a fatal dose. The team marks the area with warning flags and withdraws. By mid-morning, military units establish a perimeter at the plant boundary. Radiation reconnaissance teams begin systematic surveys using vehicle-mounted detectors. A patrol traveling the road between the plant and Pripyat records exposure rates of 1 to 3 Roentgen per hour, enough to exceed annual occupational limits in a few hours. They report findings to the plant director. No evacuation order issues. Officials debate whether readings represent localized contamination or widespread deposition. Inside the plant, operators work to stabilize the 3 undamaged reactors. Units 1, 2, and 3 continue generating power. Their control rooms lie within the same building structure as Unit 4, separated by thick concrete walls. Radiation levels in adjacent sections reach 10 to 15 Roentgen per hour. Workers rotate in 15-minute shifts to limit exposure. By afternoon, Units 1 and 2 shut down successfully. Unit 3 remains online, supplying power to the grid per orders from Moscow. At 14 hours, a government-commissioned helicopter overflies the reactor. Photographs show the building's roof destroyed, the reactor cavity open, and fires burning inside the core. Structural steel has bent and twisted. The metal-clad walls bulge outward. From altitude, the pilot estimates he can see 20 to 30 meters down into the core's graphite stack. Radiation instruments aboard the helicopter register several Roentgen per hour, even at 200 meters altitude. The photographs reach Moscow by evening. They confirm what fragmented reports suggested. Containment has failed completely. The reactor core lies exposed. Fission products escape directly to atmosphere. Estimates of released activity range from 5 to 10 megacuries, 50 to 100 million trillion becquerels, within the first day. For comparison, the 3 Mile Island accident in the United States 7 years earlier released approximately 15 curies. Chernobyl's release in 1 day exceeds that by a factor of 500,000. Academician Valery Legasov, first deputy director of the Kurchatov Institute, arrives in Pripyat by evening. His team includes reactor physicists, radiation protection specialists, and civil defense officers. They establish command posts in the city's cultural center. Initial briefings present conflicting data. Some monitors show tolerable levels, others indicate severe contamination. Legasov orders systematic surveys of the entire area. That night, monitoring teams map Pripyat street by street. Most readings fall between 0.1 and 0.5 Roentgen per hour. Elevated, but not immediately life-threatening. However, localized hotspots exceed 10 Roentgen per hour. A team finds one such spot near a school playground. A clump of moss and debris measuring 30 by 40 centimeters, reading 50 Roentgen per hour at contact. Analysis later identifies it as a particle of irradiated fuel ejected during the explosion. Dozens of similar particles scatter across the town. By midnight, medical facilities in Pripyat and Kiev begin receiving patients. Plant workers and firefighters arrive with nausea, vomiting, and skin erythema, early signs of acute radiation syndrome. Blood samples show lymphocyte depression. Doctors familiar with radiation medicine recognize the pattern immediately. Estimated doses for the most severe cases exceed 6 grays. Survival unlikely even with aggressive treatment. Moscow orders preparation for evacuation. Buses from Kiev and surrounding regions mobilize during the night. By dawn on the 27th, 1,100 buses queue on roads approaching Pripyat. Evacuation begins at 14 hours. Residents receive notice at 13 hours. Prepare for temporary evacuation lasting 3 to 5 days. Bring documents, minimal clothing and food. Leave pets behind. The announcement cites unfavorable radiological conditions. Evacuation proceeds in waves, block by block. 50,000 people leave within 3 hours. Buses depart in convoy, heading south toward Kiev region reception centers. Health physics teams monitor evacuees with handheld detectors, checking for surface contamination. Approximately 7% show readings above background. Decontamination stations wash clothing and skin with soap and water. The exclusion zone, initially set at 10 kilometers radius, expands to 30 kilometers within days. 116,000 people ultimately evacuate from the zone. Farms abandon livestock. Machinery remains in fields. The city of Chernobyl, 30 kilometers downstream along the Pripyat River, empties by May 3rd. Towns in Belarus, where the plume deposited heavily, begin evacuations in late May, after delayed monitoring, confirms contamination levels exceeding safe occupancy thresholds. Agriculture faces immediate restrictions. Milk from cows grazing in contaminated areas concentrates iodine-131, which concentrates in thyroid glands. Measurements in early May show milk samples from farms 50 kilometers northwest exceeding 10,000 becquerels per litre, 200 times the emergency intervention level. Authorities ban milk sales from affected regions. Approximately 70,000 cattle undergo testing. Those exceeding limits enter controlled. Slaughter and disposal. Soil sampling reveals the deposition pattern. Cesium-137, with a 30-year half-life, settles in a northwest band extending 300 kilometers into Belarus and beyond. Areas receiving more than 15 curies per square kilometer become long-term exclusion zones. Total contaminated area exceeds 200,000 square kilometers, roughly twice the size of Iceland. Within this zone, approximately 5 million people reside. Most remain in place, but food production, forestry and land use face decades of restrictions. The reactor continues burning for 9 days. Helicopters drop approximately 5,000 tons of material onto the exposed core. Boron carbide to absorb neutrons, dolomite to moderate temperature, sand to smother flames, lead to shield radiation, and clay to filter releases. Pilots fly through radiation fields exceeding 1,000 Roentgen per hour, making single passes before withdrawing. Cumulative crew doses reach operational limits within days. Missions continue with rotating personnel. By May 6th, core temperature measurements suggest the fire has diminished. Remote readings stabilize near 300 degrees Celsius. Emissions decrease but do not stop. Fission products continue escaping through cracks in the dropped material. Engineers debate next steps: seal the reactor permanently or attempt fuel removal. The decision favors sealing, construction of a containment structure, later called the sarcophagus. Construction begins while radiation levels remain extreme. Workers operate in shifts measured in minutes. A concrete mixing plant establishes on-site. Steel fabrication occurs in shielded areas. Remote control equipment positions structural elements. By November, a steel and concrete shell encloses the destroyed reactor. It is not airtight. Gaps allow ventilation and prevent hydrogen accumulation, but it limits further dispersion. The final inventory: 190 metric tons of uranium dioxide fuel, 900 tons of graphite moderator, and approximately 4% of the core's fission product inventory released to the environment. The remaining 96% remains inside the shelter, a radioactive mass generating enough decay heat to require active monitoring decades later. Numbers define the event's scale, but they do not explain it. Why did a reactor designed with redundant safety systems destroy itself within seconds of initiating shutdown? That question drives investigations through the following months. Moscow establishes the Government Commission on Investigation of the Causes of the Chernobyl nuclear power plant accident in May. Legasov chairs the technical working group. Their mandate: determine what happened, identify causes, and recommend actions to prevent recurrence. Evidence includes operator logs, instrument recordings, physical debris, and testimony from survivors. Initial reports blame operators. They violated procedures by running the test at low power, with insufficient control rods inserted. They disabled safety systems to prevent automatic shutdown. They ignored warnings and proceeded despite abnormal conditions. This narrative fits established patterns. Human error caused the accident. The reactor design remained sound, but Legasov's team finds contradictions. Operators followed approved test protocols. Their actions, while deviating from ideal practice, occurred within parameters the reactor's control systems permitted. If the design included safeguards against dangerous conditions, why did those safeguards not activate? Why did the emergency shutdown, the ultimate safety action, trigger the explosion? Investigations focus on the control rod design. Engineers retrieve rod fragments from the debris and examine them. The discovery of graphite tips surprises Western observers, who assume all control rods consist entirely of neutron-absorbing material. Soviet designers used graphite displacers to improve neutron economy. Why waste neutrons in water when graphite can moderate them efficiently? Mathematical modeling reconstructs the insertion sequence. When fully withdrawn rods insert, the graphite tip enters first. For the lower third of the core, water is replaced by graphite, a better moderator. Reactivity spikes. Only when the graphite passes through and boron carbide enters does absorption begin. At full power, with rods partially inserted, this effect is negligible. At low power, with rods fully withdrawn, the effect is catastrophic. Design documentation from the 1970s confirms engineers knew about the effect. A 1976 test report notes, control rod insertion may cause brief reactivity increase of up to 0.4 beta. Beta measures delayed neutron fraction, the margin between controlled reaction and prompt criticality. 0.4 beta represents a significant fraction. The report recommends maintaining minimum rod insertion to avoid this regime. Operational regulations eventually specify 30 rods minimum, but regulations did not prevent withdrawal. The reactor control system allowed operators to withdraw rods beyond safe limits if they chose. No physical interlock stopped them. No alarm announced when margins disappeared. The design assumed operators would follow rules even under pressure, even during off-normal conditions. A second flaw emerges: the positive void coefficient itself. Western reactors use light water as both coolant and moderator. If water boils away, both cooling and moderation decrease. The reaction slows. This negative feedback provides inherent safety. RBMK reactors separate functions. Graphite moderates, water cools. If water boils, moderation continues, but cooling decreases. Reactivity increases. The reactor accelerates. Design calculations predicted this behavior. Engineers judged it acceptable because normal operations maintain stable water flow and temperature. Steam production stays constant. The positive void coefficient activates only during transients, brief controlled events. But the April test created conditions designers never analyzed: low power, minimal control rods, and sudden coolant flow reduction. In that regime, positive feedback dominated. The investigation identifies multiple contributing factors. Test protocol inadequacies. The original procedure assumed normal operating conditions. Delays and operational demands pushed execution into unvalidated territory. No analysis considered the combination of xenon poisoning, reduced power, and minimal control margin. Operator training gaps. Crews learned RBMK behavior at rated power. Low power dynamics received minimal coverage. Few operators understood the positive void coefficient's implications. None knew about the control rod insertion effect, design flaws. The graphite tip control rods and positive void coefficient created instabilities the reactor could not tolerate. Emergency protection systems, instead of ensuring safety, accelerated destruction. Regulatory oversight. Safety authorities approved the test protocol without independent analysis. They did not verify operators maintained minimum control margins. They accepted manufacturer assurances about reactor stability without demanding proof. Legasov presents findings to the International Atomic Energy Agency in August. His report, delivered in Vienna, shocks the audience. The reactor design contained fundamental flaws. Soviet regulatory culture prioritized production over safety. Operators received inadequate training. A series of decisions and conditions, none catastrophic alone, combined to create disaster. Western observers note the revelations with concern. Soviet reactor designs differ fundamentally from Western types, but the accident reveals universal lessons. Complex systems fail in unexpected ways. Multiple barriers prevent accidents only if each barrier functions independently. Operators need training for off-normal conditions, not just routine operations. Safety culture requires questioning, reporting, and learning from near misses. Soviet authorities implement changes. Control rods receive boron carbide extensions, eliminating graphite tips. Manual control rod withdrawal limits install at remaining RBMK reactors. Operational regulations strengthen, requiring minimum control margins at all power levels. Operator training programs expand to include low-power dynamics and accident scenarios. By 1990, all operating RBMKs incorporate modifications reducing the positive void coefficient and improving emergency shutdown speed. But the fixes cannot reverse the fundamental design choice. RBMK reactors remain graphite-moderated, water-cooled, and vulnerable to conditions their designers never fully explored. When the Soviet Union dissolves in 1991, 11 RBMK reactors operate in Russia and Lithuania. Over the following decades, economic and political pressures keep them running despite international concerns. Chernobyl's Unit 3, which shares a building with the destroyed Unit 4, resumes operation in December 1986. It runs 14 more years. International pressure and financial incentives from the European Union eventually secure closure. On the 15th of December 2000, operators press the shutdown button for the final time. The last RBMK at Chernobyl goes cold, but the design lives on. As of 2025, 10 RBMK reactors remain operational in Russia, generating approximately 8,000 megawatts electrical. Modifications have improved safety margins, but the core characteristics persist. They burn hot because graphite moderation allows higher power density. They burn hot because the positive void coefficient accelerates reactions during transients. They burn hot because the original design optimized efficiency and construction cost over inherent safety. The trade-off was explicit. Engineers knew graphite moderation improved neutron economy. They knew positive void coefficient meant instability during certain transients. They calculated risks and judged them acceptable under controlled conditions. What they missed, the boundary between controlled conditions and disaster, was thinner than calculations suggested. Xenon poisoning, low-power operation, and inadequate control margins could combine in ways simulations never explored. Technology embeds choices. The RBMK embedded a choice: accept operational complexity and instability in exchange for construction simplicity and fuel efficiency. For 15 years, that choice appeared sound. Reactors operated, produced power, and experienced only minor incidents. Then, in 83 seconds on a spring morning, the accumulated risks manifested. Design met reality, and reality redefined what was possible. November 1986. Snow falls on Chernobyl. The destroyed reactor now sits beneath a steel and concrete shell, hastily erected over 6 months by crews working in shifts measured in seconds and minutes. They call it the sarcophagus, a tomb for Unit 4. It is not designed to last. Gaps remain. Steel beams rest on rubble. Concrete pores occurred in radiation fields that would kill unprotected workers within an hour. The structure's purpose: stop further releases, contain the wreckage, allow time for longer-term solutions. Inside, 170 tons of irradiated fuel remain, mixed with melted metal, pulverized concrete, and dropped covering materials. Decay heat still warms the mass, though no longer enough to sustain fire. Fission products continue decaying. Cesium-137 emits gamma rays for 300 years. Strontium, 90 beta particles for 300 years. Plutonium, 239 alpha particles for 24,000 years. The inventory represents 96% of the core's original radioactivity, approximately 100 million curies. External monitoring continues. The 30-kilometer exclusion zone remains closed except for authorized workers. Radiation levels vary widely. 10 microroentgen per hour in some locations, 1,000 microroentgen per hour in hotspots near the reactor. Forests show damage from acute exposure. Red Forest, directly west of Unit 4, received doses exceeding 100 grays. Pine trees died within weeks, turning orange-red before defoliation. Soil contamination in this zone exceeds 500 curies per square kilometre. Long-term health studies begin. The most immediate concern, thyroid exposure from iodine-131 in children who drank contaminated milk during April and May. Iodine concentrates in thyroid glands, delivering localized doses. Estimates suggest 50,000 children in Ukraine and Belarus received thyroid doses exceeding 1 gray. Baseline thyroid cancer rates in children are approximately 1 per million per year. Studies will track increases over decades. By the late 1990s, data confirm elevated thyroid cancer rates. Between 1990 and 2005, approximately 6,000 excess thyroid cancer cases occur in exposed populations, primarily in individuals under 18 at the time of exposure. Early detection and treatment keep mortality low, fewer than 15 deaths, but the increase is statistically undeniable and causally linked to Chernobyl. Broader population health effects remain controversial. Studies estimate that cleanup workers, liquidators, numbered approximately 600,000 between 1986 and 1990. Doses varied enormously. Early responders received tens of grays. Later workers, benefiting from improved shielding and remote equipment, averaged 0.1 gray. Statistical analyses attempt to correlate exposure with cancer mortality, but confounding factors, smoking, alcohol consumption, diagnostic practices, record quality, complicate conclusions. Estimates of eventual cancer deaths attributable to Chernobyl range from 4,000 to 90,000, depending on methodology and assumptions. Economic impacts are easier to quantify. Direct costs, evacuation, decontamination, reactor enclosure, medical care, monitoring, exceeded $18 billion by the mid-2000s. Indirect costs, lost agricultural production, abandoned infrastructure, exclusion zone maintenance, continue indefinitely. Belarus, which received 70% of fallout, estimates total economic damage at $235 billion through 2015. Ukraine and Russia report similar long-term burdens. The sarcophagus itself deteriorates. By 2000, structural surveys reveal cracks, corrosion, and instability. Winter snows load the roof. Summer heat expands steel, radiation degrades concrete. Engineers calculate that roof collapse becomes likely within years. If collapse occurs, dust-containing fuel particles could become airborne again, spreading. Contamination beyond current boundaries. International funding supports a replacement. The new safe confinement, a steel arch spanning 270 meters, begins construction in 2010. Built on tracks 300 meters from the reactor, it will slide into position over the existing sarcophagus. Completion occurs in November 2016, 30 years after the accident. The arch weighs 36,000 tons, cost $2.1 billion, and is designed to last 100 years. Beneath the arch, remote control equipment begins dismantling the old sarcophagus. Robots cut steel beams, sort debris, and package radioactive materials for disposal. The goal? Eventually remove the fuel-containing masses and transport them to secure storage. The timeline extends decades. Work proceeds in 15-minute intervals. Radiation limits still govern every action. Outside the exclusion zone, life adapts. Villages within 30 kilometers remain abandoned. Nature reclaims structures. Trees grow through roofs, vines cover walls, and wildlife populations expand. Przewalski's horses, introduced as part of a rewilding program, roam the empty town of Pripyat. Wolves, lynx and boar thrive without human presence. Radiation persists. Cesium levels in mushrooms, berries and game animals exceed food safety limits by factors of 10 to 100, but ecosystems function. Organisms tolerate contamination levels lethal over acute timescales, but sustainable over generations. The exclusion zone becomes an unintentional experiment in long-term contamination ecology. Scientists study mutation rates, population genetics, and adaptive responses. Results show mixed effects. Some species exhibit higher mutation frequencies, others appear unaffected. Local selection may favor radiation-resistant variants, but evolutionary timescales are too short for conclusive evidence. The zone is neither dead nor pristine. It is changed, altered at molecular and ecological levels. Tourism begins in the 2000s. Authorized tours enter the zone under strict protocols: no touching surfaces, no entering buildings without permission, mandatory dosimetry, and decontamination screening on exit. Visitors see Pripyat's empty apartment blocks, the abandoned amusement park, and the reactor arch. Dosimeters record exposures of 5 to 20 microsieverts per day, equivalent to a chest X-ray or transcontinental flight. Short visits pose minimal risk. The experience is surreal, a frozen moment from 1986, preserved by contamination too persistent to allow return, yet too low to prevent brief presence. 40 years later, in 2025, the site remains active. Workers maintain the new safe confinement, monitor radiation, and dismantle internal structures. Plans for complete fuel removal extend to 265, 300 years after the accident. Costs continue. Ukraine spends approximately $100 million annually on exclusion zone management. International donors provide additional funding for specific projects. The destroyed reactor is no longer a crisis. It has become a condition, a long-term chronic situation requiring perpetual management. The fuel will outlast any institution currently overseeing it. The isotopes decay on schedules indifferent to politics, economics, or human attention spans. Cesium's 30-year half-life means that by 2086, 100 years post-accident, activity will decrease to roughly 1/8 of initial levels. Still significant, still requiring control. This is the RBMK's final lesson. Some choices create obligations measured not in decades, but centuries. The reactor burned hot for efficiency. It burned hot from design compromises. And when it failed, it burned for 9 days, creating a legacy that outlasts nations. The new safe confinement stands in the afternoon light, its steel surface reflecting clouds. Workers exit in small groups, dosimeters clipped to chest pockets. Readings show exposure well within limits, progress measured in microsieverts instead of grays. Instruments have evolved, risks remain. A memorial plaza sits 500 meters from the arch. Black granite lists the cities and villages evacuated, 187 locations. Names carved in Cyrillic mark, a geography that no longer exists on functional maps. Pripyat, Chernobyl, Kopachy, Zalicia. Places where postal codes route to administrative offices in Kiev, but where no one receives mail. On the plaza, a metal sculpture depicts hands releasing birds. Nearby, a dosimeter display updates continuously, showing current background, 0.3 microsieverts per hour. Roughly double natural levels elsewhere, low enough for brief visits, high enough to remember. Inside the arch, decommissioning continues. Estimated remaining inventory, 165 tons of fuel-containing material. Removal rate, approximately 3 tons per year. Simple mathematics projects completion decades hence, assuming technology, funding, and political will persist. History suggests caution in those assumptions. The RBMK burned hot because designers chose thermal efficiency over operational simplicity. They chose construction speed over inherent safety margins. They chose present needs over future risks. These were not irrational choices. They optimized for the constraints Soviet planners faced in the 1970s. Limited uranium enrichment capacity, growing industrial demand, pressure to deploy quickly. The RBMK solved those problems elegantly, but elegant solutions can contain fatal flaws, invisible until conditions expose them. The positive void coefficient created instability the design barely controlled. The control rod graphite tips inverted shutdown logic in untested regimes. The modular construction allowed scaling, but prevented robust containment. Each choice made sense in isolation. Together, they defined a reactor that operated successfully for years, then failed catastrophically. 40 years later, 10 RBMKs still operate in Russia. They generate 7,800 megawatts, approximately 2% of the nation's electricity. Modifications since 1986 have reduced risks. Graphite tip rods are gone. Positive void coefficient is partially mitigated. Emergency shutdown systems are faster and more redundant. Operational regulations enforce strict control margins. Training programs emphasize off-normal scenarios. Yet the fundamental architecture persists. Graphite moderation, pressure tube cooling, positive void coefficient. The characteristics that made RBMKs burn hot remain embedded in their design. Modern safety systems constrain these characteristics, limit their expression, prevent combinations that lead to instability. But constraints require vigilance, maintenance, and institutional memory. Institutional memory fades. Operators who remember 1986 retire. Engineers who redesigned safety systems move on. Regulators who insisted on modifications lose budget battles. The exclusion zone becomes a tourist attraction, its seriousness diluted by selfies and souvenir dosimeters. Time erodes urgency. This is the final contrast. The isotopes remember. Cesium-137 decays with mathematical precision, indifferent to anniversaries. Strontium-90 continues emitting beta particles whether observed or ignored. Plutonium-239 will remain radioactive long after humanity forgets Chernobyl ever occurred. The physics persists. A monitoring well northeast of the reactor shows groundwater contamination at 200 becquerels per litre, 40 times the intervention level for drinking water. The plume migrates slowly toward the Pripyat River. Models predict it will reach the river in decades. From there, it flows to the Dnieper River, which supplies water to 30 million people. Containment barriers exist. Slurry walls, pumping wells, treatment systems. But they require operation, funding, and attention across timescales longer than most institutions survive. Documentation fills archives. Technical reports describe every measurement, every modification, every lesson learned. They sit in Kiev, Moscow, Vienna, repositories of knowledge intended to prevent recurrence. But archives do not enforce safety. People do, and people forget, cut budgets, defer maintenance, accept risks that previous generations rejected. The sarcophagus, the arch, the exclusion zone, the monitoring programs all represent commitments to manage consequences. They do not eliminate hazards. They contain, monitor, and control. For how long? The design life of the new safe confinement is 100 years, a century. By then, cesium activity will decrease to roughly 3% of current levels. Still substantial, still requiring oversight. Who will maintain these systems in 2116? What state will govern? Ukraine? What institutions will remember why the arch exists? The questions have no answers, only assumptions. We assume continuity, stability, and resources. History suggests caution. The reactor design embedded choices about risk, efficiency, and safety. Those choices created value: electricity, jobs, energy independence, but also obligations. Obligations that extend far beyond the reactor's operational life, far beyond the lives of its designers, far beyond the survival of the state that built it. This is what it means to burn hot. Not just intensity of operation, but persistence of consequence. The RBMK achieved its purpose. It generated power efficiently, scaled quickly, and served Soviet energy needs for decades. It also created a 30-kilometer exclusion zone, displaced hundreds of thousands, contaminated territories across 3 nations, and imposed management obligations lasting centuries. Were the trade-offs worth it? The question is meaningless. The choices were made, the reactor operated, the accident occurred, and the consequences persist. Evaluation belongs to those living with outcomes. Farmers banned from their land, families relocated from ancestral villages, workers spending careers managing contamination, children born into regions where mushrooms still exceed safety limits 40 years later. Technology does not exist apart from consequences. Every design embeds values, priorities, and assumptions. The RBMK optimized for rapid construction and fuel efficiency. It assumed controlled operations, trained operators, and stable institutions. It assumed that brief instabilities could be managed, that positive feedback would remain bounded, that regulations would be followed. Some assumptions held, others failed. The reactor burned hot because its design allowed it. The reactor exploded because its design permitted it. The exclusion zone exists because design could not prevent it. On April 26th each year, survivors gather at memorials. They light candles, lay flowers, and remember. Not just those who died, though they are honored, but also the choices, systems, and assumptions that shaped outcomes. They remember that complex systems fail in complex ways, that safety requires more than procedures. It requires culture, vigilance, and humility, that consequences often outlast intentions. The arch stands, monitoring continues, isotopes decay, and 10 RBMKs still burn, controlled by systems learned from Chernobyl, operated by engineers who study its lessons, regulated by authorities who remember. They burn hot. They always have. That was the design.